Ladies and gentlemen, distinguished guests, good morning. It is with great pleasure that I stand before you today to share some exciting developments in the field of computer vision and tracking. In our quest to push the boundaries of tracking technology, we present to you Procontext, exploring progressive context transformer for tracking. This groundbreaking research, conducted in collaboration with the esteemed DNO Academy at Alibaba Group and Carnegie Mellon University, has yielded significant advancements in the field. We invite you to explore our work and witness firsthand the capabilities of Procontext. The code and additional resources are available on GitHub at the following link. First, I am here to discuss a crucial aspect of computer vision: visual object tracking, VOT. The objective of VOT is to predict the location of a target object in subsequent frames, enabling accurate tracking of moving objects in real time. This technology plays a vital role in enhancing situational awareness in various applications, including human-computer interaction, HCI, and video surveillance. One of the key challenges in VOT is dealing with dynamic changes in object appearance. To address this, adaptive models are employed, allowing tracking systems to learn and update the target's visual features over time. By continuously adapting to appearance variations such as scaling, deformation, and changes in appearance, these systems maintain accurate tracking performance. Another critical aspect is discriminative target identification, especially in scenarios where there are similar instances. Accurately identifying and tracking the desired target amidst distractors is crucial. This is achieved by leveraging discriminative features and similarity metrics, enabling the differentiation of the target from its surroundings. By employing such techniques, robust tracking performance can be achieved even in challenging scenarios. As shown in the figure, proposed Procontext tracker encodes both temporal and spatial context through a template group composed of static and dynamic templates, providing a comprehensive and progressive context representation. The model leverages a context-aware self-attention module to learn rich and robust feature representations, while a tracking head is used to update dynamic templates and generate tracking boxes. The main contribution of this paper are threefold. First, Procontext is the first work to exploit progressive context encoding over dynamic temporal and varying spatial in transformer-based tracking. It builds a bridge between classical contextual tracking and context-free tracking, and investigates how to encode context in real-time tracking. Second, Procontext revises the VOT backbone, adding more static and dynamic templates and improving context-aware self-attention to exploit multi-temporal and multi-spatial information. With progressive template refinement and updates, it alters the token pruning to seamlessly bring contextual encoding into transformer-based tracking. Third, Procontext achieves SOT performance on large-scale tracking benchmarks, including TrackingNet and Go10K. Despite expanding long-term temporal and multiscale spatial information, Procontext can perform context encoding and tracking in real time at 54.3 FPS. More specifically, given video frames and an initial box, we crop the templates at different scales to generate static templates. Similarly, the dynamic templates are produced to encode more object appearance changes during tracking process. We also crop the area centered on the box at the previous frame to get search area X, assuming that the target object appears in the adjacent region of the last known location. Based on the expanded static templates and dynamic templates, we modify the VIT for representation learning. All the templates and search tokens are concatenated and input coherently into the context-aware self-attention modules. Equation 1 shows that the context-aware self-attention module can encode both dynamic temporal and variable spatial information from all static and dynamic templates. Furthermore, we modified the token pruning technique to accelerate Procontext. The purpose of pruning is to reduce computational costs. We take into account all static and dynamic templates. This allows foreground tokens to remain similar to dynamic templates, even after significant changes in appearance, ignoring the search tokens for noisy background patches. The similarity matrix is calculated using queries from static template tokens and dynamic template tokens, and keys from search tokens. Finally, we only keep the search tokens for the top elements of the similarity matrix. The pruned tokens are replaced with zero padding and then fed to the tracking head. The tracking head firstly reshaped the tokens into the 2D feature, and then performed tracking using score head, offset head, and size head. The score head is trained using a Gaussian kernel with focal loss, which is shown in EC2 and EC3. The final bounding box coordinates are trained with E loss and L1 loss. Finally, the total loss is shown in EC5. The proposed Procontext achieves SOTA performance on both TrackingNet and Go10 datasets. Table 1 shows the superior performance of our tracker under different pre-training strategies. When pre-training with the ImageNet1 dataset, Procontext achieves the best results among all compared methods. By utilizing MA pre-training, Procontext outperforms the recent SOTA method, OSTRAC, by 0.9% for AO on Go10K. We also evaluate our model on the TrackingNet dataset, and it demonstrates better performance than the SOTA methods. We conduct an ablation study on the .10 benchmark and report performance on the validation split. In Table 2 and Table 3, we investigate the number of templates. From Table 2, we observe that all models with multi-scale static templates enhance performance since Procontext can effectively encode spatial context. Notably, Procontext with only one additional static template achieved the best result, plus 1.6% in AO and plus 1.9% in SR, suggesting that more static templates may introduce additional noise. From Table 3, it was evident that adding dynamic templates improved performance by 1.2% in AO and 1.4% in SR, demonstrating the effectiveness of temporal context. Table 4 presents the effects of the token pruning module. The keeping ratio indicates the proportion of reserved tokens after the pruning operation. When R is set to 0.7, Procontext improves AO by 1.1% and reduces GFLOPs by 16.5%, achieving a good trade-off between computation cost and accuracy. That's all for the talk, and thanks for your attention.